is using this diagram. Look, negative, positive, positive, negative. That is, it is series connection but opposing. So 0.7 minus 0.4, you will get 0.3 here. This is the boundary of active region. If that reduces into 0.2, you are certainly in saturation. 0.1, very much deep into saturation. And that is how, once we reach the saturation level, we are working with beta forced. Any questions from here? Yes. That's the boundary of active. Yes. But instead of remembering this BCB, it's a very difficult thing to remember. You can easily get confused because there is a reverse bias there. You can, by forcefully, you can believe that your collector needs to be negative with respect to base. That is not the case. For example, let me try to share you my screen. Your collector base is at 0.7. Emitter is at 0. Your collector is at 10 volt. Is it reverse bias or forward bias? Collector is N, base is P. Talk about collector base junction. Okay, talk about base. Is it forward bias? That is fine. What is VCB? 10 minus 0.7, that is 9.3 volt. It is not that 9.3 that you need to look. Is it better now? I hope. Can you see now? Now, collector is N, more positive with respect to base by 9.3 volt. Certainly, it is a reverse bias. You can reduce that to 9 volt. Still, collector base is reverse bias. You can put a 0 volt. Your VCB is still 0.7 reverse bias. You can go up to 0.4 here. That is the minimum value at the collector we need to make collector base in reverse bias. Okay, this is, I have added this particular slide diagram into the slide to illustrate this property. And you may experience some kind of a problem there if you really want to understand. Look, 0, that is the origin, x-axis, collector emitter voltage, and the same diagram is magnified in the second one. Sorry. Now, that is the origin. Origin is still in the same place. The voltage is incremented. It is a magnified region, 0.1, 0.2, 0.3, 0.4. And this clearly indicate that up to between 0.3 onwards, you get active region, that is VCE. Anything less than that, you are in saturation. Okay, cutoff is that region. So I'm going to move on unless there are questions. I have asked everyone to work out this problem. Did anyone try it out? This is problem 4.1. Case 1. Find VBE. Voltage at the base 0.7, voltage at the emitter is 0. VBE 0.7 volt. Is it good enough to decide? Is it in active saturation or cutoff? No, not yet. We need to verify VCE. Voltage at the collector is 0.7 and voltage at the emitter is 0. You get 0.7 volt. This is VBE 0.7 and VCE greater than 0.2. Definitely this is active. Let's take case 2. Find VBE. Voltage at the base is 0.8 minus 0, that is 0.8 volt. This is not good enough to decide if it is saturation, active, or cutoff. We need VCE. Voltage at the collector is 0.1 minus voltage at the emitter is 0. 0.1 minus 0, 0.1 volt. Certainly, this is in saturation. Why? Your VCE is less than 0.2. Let's look into case number 3. Find VBE. Voltage at the base is 0 minus voltage at the emitter is minus 0.7. That is plus 0.7 volt. Next, let's see VCE. Voltage at the collector is 0.7 volt minus voltage at the emitter is minus 0.7. Minus plus, it is 1.4 volt. So this is certainly active. And I want all of you to work out all the remaining problem by yourself. It's for me working out again and again doesn't make any sense at all. I'm leaving it for you. The second problem, problem 4.10, IEIB, you can work out collector current, that is 1 milliampere minus 50 microampere. So IE, IB, IC are known, you can work out beta and alpha as well. Did we work out this problem? Yes, I think. Did we work it out?
What number is that, sir?
This problem has no number. This is slide number 27.
So I think we did go through it.
Yes, we did. What about this one? This one as well, I believe.
Yes, we're doing it last week.
Okay. We did the early effect. And we described the effect of early effect. Then did we work out this problem? Okay, I think this is where we stopped. BJT circuit DC first order analysis. We summarized what is first order analysis in previous class. A first order analysis compromises the accuracy for speed and insight. So we may use the following assumption. VBE equal to 0.7 for a conducting transistor. VCE 0.2 for a saturated transistor. Okay, now go through this table. VBE less than 0.7, IC equal to 0, it is cut off. And here I could even write IC equal to 0 means VCE equals VCC. You can add it by yourself, by hand. Because collector current is 0 means there is no voltage drop at the collector. That means supply voltage will be your VCC. VCE will be your VCC. So VBE less than 0.7, VCE equal to VCC, certainly it is a cutoff. VBE approximately 0.7 and VCE greater than 0.3, it is active region, and VBE approximately 0.7 and VCE is 0.2 is triode, that is saturation mode. Now, I want you to have a look here into this column. This column, VBE, all the three conditions nearly equal to 0.7. Therefore, looking for VBE to find out if the transistor is in saturation, cutoff, or active, you will never get an idea at all, because all the three conditions, VBE remains at 0.7. But looking at this, look at the second column. VCE equal to VCC, that is cutoff. VCE 0.3, that's a boundary of active. VCE 0.2, deep in saturation. And this is going to give you fairly good idea whether BJT is in saturation, cutoff, or active. Okay, BJT circuits at DC first order analysis. Example 4.4. Analyze the circuit to determine voltage at all the nodes and the current through every branch. Beta is 100. Okay, a problem like this, we can start working out with what we know already. That is, you pick it up from the diagram. So, how do you work out value of beta is 100? It is given. We need to start with something solid, something we know for a certain thing. Voltage at the base 4 volt. That is something solid. Now we can work out voltage at the emitter. Can we work out voltage at the collector? No way, because voltage at the collector could be any value from 10 volt. If it is voltage at the collector, 10 means it is cut off basically, or any lower value up to 0. less than 4. It is still fine. So looking at finding out the collector voltages, it is something that nobody can predict what it is, but you can work out at the end if you go through the proper steps. But voltage at the emitter is voltage at the base minus VBE. That is 4 minus 0.7, you get 3.3 volt. That is voltage at the emitter. If you know voltage at the emitter, 3.3 volt, the other end of the resistor is at ground. Therefore, you can work out emitter current. Emitter current is voltage at the emitter minus 0 divided by RE. That is basically 3.3 divided by 3.3K. It is going to be 1 over K is milliampere. That is voltage at the emitter. Sorry, emitter current. We can work out base current. Base current is emitter current divided by beta plus 1. That is 1 milliampere divided by 101. Somebody please calculate it for me. (9.901 microampere). Now you can work out collector current. Collector current is 1 milliampere. That is emitter current minus base current. So 1 milliampere minus 9.9 microampere. So we found collector current as well. What else we need? We found all the currents. Voltage at the base is 4 volt given. Voltage at the emitter is voltage at the base minus 0.7. You got 3.3. Voltage at the collector. Okay, that is something we don't know. There is only one way to find out voltage at the collector. That is, you have to work out from something solid, something we are certain of. You have to work from there because VCE could be any value more than 0.3 and VCC. So you cannot work from emitter voltage to the collector. You cannot work out from base to the collector as well because we don't know. We only know there is a reverse bias. So the only way of finding voltage at the collector is VCC minus IC times RC. Remember, current times voltage is a voltage drop. So supply voltage minus voltage drop across RC will give you collector voltage. 10 minus collector current is 990.1 microampere times 4.7 K. Somebody verify if the answer is right.
Yes, sir.
Can I move on?
Yes, sir.
Okay, BJT circuits at DC. The summary. In fact, here it is given step by step. Voltage at the base is 4 volt. Step 1, find the voltage at the emitter. Step 2, find the emitter current. And step 3, find the collector current, or you can find the base current, then find the collector current. Last step, find the collector voltage. And this is the step we follow all the BJT problems. Sometime in this case, we are lucky, voltage at the base is given. In some cases, it may not be given. We may have to find out. We will reach there soon. BJT circuit at DC. Analyze the circuit to determine the voltage at all nodes and current through each branch. Okay, this problem, I'm not going to work out this one because it is perfectly the same as like before. Why? Okay, let's try to work out, because there is some kind of a surprise is awaiting you there. This is the same BJT circuit. Look at the resistors, 4.7K, 3.3K, and that is ground. What is the difference? Previously, we had 4 volt at that point. Sorry, I will put that. This is the only difference. Same BJT circuit, collector resistance 4.7K, emitter resistance 3.3K. So let's follow the step. First, voltage at the emitter is 6 minus 0.7 equals 5.3 volt. Next step, emitter current is 5.3 minus 0 divided by 3.3K. You get 1.606 milliampere. What about the base current? Base current is 1.606 milliampere divided by beta plus 1/101. That is 15.90 microampere. That basically means collector current equals 1.606 milliampere minus 15.9 microampere. So your collector current is supposed to be 1.59 milliampere. Let's try to work out voltage. We need voltage at all the node. Let's work out voltage at the collector. Voltage at the collector is 10 minus collector current 1.59 milliampere times 4.7K. This is going to be 2.527. Now we need to go back and verify what is voltage at the emitter. Voltage at the emitter was 5.3 volt. What about the voltage at the collector? 2.53. Do you see any problem? Is everything fine there? What voltage add up to 10? No, it's nothing like that. But there is a problem. Work out VCE. 2.53 minus 5.3. You get an answer. How much? Do you think it is possible VCE going negative? What is the condition we learned regarding VCE for an active operation?
It must be greater than 0.3 volt.
It must be greater than 0.3 volt, and now we are not getting. So voltage at the collector can go as low as 5.3, right? Then VCE becomes 0 already. You cannot make it negative. It will never go negative. In this case, what happens is your collector current that is flowing, it will be same as, in this case, the collector current is called IC SAT. That is going to be equal to VCC divided by RC plus RE. Or basically, this VCE can go up to 0 and it will stop. In this case, 10 divided by what is 4.7 plus 3.3? Isn't it 10K? No. So your current is going to be 1.25 milliampere. Your current is going to be, collector current is going to increase up to 1.25 milliampere, and after that, current cannot increment. This is a condition. Base current increases, collector current fail to respond. We have learned it. We have learned that before. See, this current is not possible. because BJT is entering into saturation. Time for questions. Yes. Sorry, I didn't get the question. It can be any, it can be more than 0.3, then there is no problem. Then it is saturation. For the test, of course, then there is going to be a part of question will work out what is the maximum collector current possible in this circuit, or maybe there is a question like decide if this BJT is active cutoff or saturation. Usually, if it is saturation, there will be a supplementary question like calculate IC sat. That is 4.5, where we found, that is why you can see here. It is marked with a cross, thinking it is a saturation condition. BJT circuit at DC, analyze the circuit to determine voltage at all nodes and current through each branch. See, all the questions we have seen so far are identical, is it? Let's have the BJT circuit diagram, 10 volt. It is still 4.7K. And it is still 3.3K at the emitter and a ground. Where is the difference? There is only one difference. Question didn't give you value of beta. Okay, let's try to work it out. This question is not giving value of beta, but we don't just give up. If you don't work out, because there is no value of beta, you still get a 0. Okay. What's the difference between the previous circuit and this circuit? Well, there is only one difference. That is, in the previous cases, voltage at the base was, initially it was 4 volt, then second part of the question, it was 6 volt, where there is a saturation happening. Now it is a ground at the base. Okay, ground at the base, don't give up. Why? We know ground is 0 volt. Okay. If this BJT needs to conduct, what must be the voltage at the emitter? That is at this point. I want someone to answer me. If this BJT circuit needs to conduct, what must be the voltage at the emitter?
0.7, sir.
Don't just sing a song. Think before you answer. Do you think if you put a 0.7 like that, this BJT is going to conduct? Where is N? Do you think this BJT is going to conduct? P with a 0 and N with a 0.7. It is reverse bias. This BJT cannot conduct at 0.7. Do you want to modify your answer?
Yes, I think it's negative 0.7.
Negative 0.7. Now, look at the diagram very carefully and tell me, is it possible to have a negative 0.7 there? Pick up from the clue I gave you. Anybody can pick up the clue. There is a semiconductor junction there. You are not picking the clue that I am giving. Pick up the clue.
So I think the emitter is at ground, sir. So the voltage there is 0 volts.
What is the reason? Man, what are you talking about? Where is the emitter? That is emitter. This is base. That is collector. Is the emitter and base connected together? Remember, guys, you need to get involved. If you are trying to learn something, there must be a two-way action. Now tell me, what is the voltage at this point?
It's 0 volts.
If it is 0 volt, what could be the voltage there? What is the voltage at this point?
Zero. It's also 0.
Then do you think it's possible? Do you think it is possible?
No, sir.
So your initial assumption that there was a negative 0.7, that assumption is not valid. So if this voltage is 0 and that voltage is also 0, voltage at the emitter will remain at 0 volt. That means there is no base current, or IB is 0. IE is 0 and IC will be 0. And in this case, what is your VCE? Collector current is 0. Voltage at the collector is same as VCC. Voltage at the emitter is 0. So your VCE is same as VCC.